electric vehicles. So something very simple is, okay, if you have a problem of CO2 emission, how to solve this problem is, one, reduce the quantity of fuel that you consume, so improve fuel consumption. Second, don't use fuel that contain carbons, because the CO2 comes from the carbon from the fuel. So one, spend less fuel. Second, use fuel which does not have any carbon. Something important I would like to point out here is this refers to tailpipe CO2 emissions. What means are the CO2 emissions that are produced during the utilization of the fuel. So it does not take into account the CO2 emission that has been involved to have the fuel in the vehicle. So if in the future the regulations are expanded to well-to-wheel emissions, taking into account not only the emissions produced from the tank, from the utilization, but also including production of the fuel and transportation, the picture will be still even more complicated. And for example, for the case of electric vehicles, and it's not only that they are not able, that they don't produce CO2 while we are using an electric vehicle, we will need to consider also which is the CO2 involved to produce this electricity and to put this electricity in the car. With respect to these pollutant emissions, other pollutant emission that has more a local, it has also a global, but has more a local effect, so it's very important where they are emitted. We have also some data since 1990 to 2013, 2014. So we can see how mainly the different pollutant emission has been reduced. Why this has happened? This has happened mainly due to the different regulation that has been introduced. And in this case, I have put here some arrows to indicate the different regulations in Europe, in that case, from Euro 1 to Euro 5. So I have highlighted two of them. I have highlighted particulate matter, because later part of the presentation will go to particulate matter, and also NOx emission. And we can see here there is something very interesting here. That is, at the beginning, NOx were reduced very quickly, but then there is a point here that NOx are not reduced as quickly as before. However, at the beginning, particulate matter were not reduced much, but later on, particulate matter started to reduce. These are the data. So why is that? My opinion is that this is due because the regulation came in place to reduce both NOx and particulate matter, and there is a famous trade-off between NOx and particulate matter, which means usually whatever you do in the engine to reduce NOx most likely will increase PM, and whatever you do in the engine to reduce particles will increase NOx. So that's the reason why, okay, you keep reducing particulate matter, but not as quick, but you are not able to reduce NOx as quicker as before. Okay, we will come back to this trade-off later on. So how we have been trying to attack or to address this challenging. So from one side, we have the fuel. As we mentioned before, if we are able to utilize fuels who has low carbon or no carbon, we will have a benefit on CO2 and greenhouse gas emission. And if we are able to find fuels that burn cleaner, we will be able also to solve the issue with pollutant emissions. Another option is try to modify the combustion system to be cleaner, or try to use new or alternative powertrains. Another option is, okay, you have tried to go with the fuel, you have tried to make the combustion cleaner, but still there are emissions that are produced. So, okay, try to go to the exhaust when the emission has been already formed and try to reduce them. Okay, we have not been able to reduce the formation, but now we are going to trap or we are going to distract them. So what I believe that we have been doing different here is that we have taken a very system approach, and we believe that it's not okay with just take one of the alternatives and do resharing one of them, but we need to take care how a new fuel is affecting to our engine and is affecting, for example, our after-treatment system. So we think it's not a competition between the three approach. We need to be able to find synergies between the three approach to be able to fulfill the greenhouse gas emission and the pollutant emission regulation and to avoid any human health or environmental effects as a consequence of that. Okay, this is, I think, an important point of what we are doing here. When we have a fuel, sometimes we just use the fuel directly in the engine. And then sometimes we also can use the fuel in the exhaust to help work the after-treatment system. There are other times that our fuel might be not good enough. And then what we are doing is we are trying to have some processes. In that case, I will talk a bit more in detail on that, about, for example, reforming. That let's say that we upgrade this fuel or we convert the fuel to something else, and then we try to see or to assess how these products, in that case could be hydrogen, are able to work either when you feed the engine with them or when you feed the after-treatment engine with them. So it's like we are not only coming with a fuel and check how the fuel works in the engine. We also try to understand how the fuel will work in the after-treatment, and if not good enough, we will try to upgrade or to transform the fuel and evaluate how does it work. So based on that, I have here the best example, the first example that we have been able to find these synergies. So for those of you who are not many related to this after-treatment system, here I have put one example of a diesel oxidation catalyst. If you have a diesel car, all of you will have a diesel oxidation catalyst in your car. What the catalyst is doing? From the engine, you have some carbon monoxide, you have some unburned hydrocarbons, and then we will have some catalytic reaction in the catalyst and be able to transform the CO and unburned hydrocarbons, okay, local pollutant emissions, to CO2 and water that does not have this local effect. So our objective is to be this catalyst to be able to work as efficient as possible, so to be able to convert most of all of the emissions for a large range of temperature. So for example, when you are driving in the city, usually your engine is a bit cold. So usually you have higher CO and unburned hydrocarbon emissions. So if you have a catalyst that is not able to work at cold conditions, you are not doing the job because your engine is emitting more pollutant emissions, and then the catalyst is not working, and then you are in a city when you have higher population level. So what I want to say with that is like, if this is the emissions output of the catalyst with respect to temperature, so there is a region of temperatures that the catalyst will not be efficient, but later on, when the temperature increases, your catalyst will work very efficiently. So what we have tried to do, we have tried to investigate how we make the catalyst efficient to lower temperature. Moving to the left. Then we have done some tests with some fuels, in this case with some biodiesel, and we have observed how if you take the catalyst with diesel, and if you compare with biodiesel, the catalyst is more efficient at lower temperature. So as we can see here, we are able to provide a fuel that not only has some CO2 benefits. Not only is able to reduce the emission level in the engine, but also it makes the catalyst to work better. So in the past, we have also had the experience of some fuels that behave very well in the engine, but later poison the catalyst. So, okay, there is no point because, okay, it's not enough. The fuel needs to also have good performance in the catalyst. Or in the past, we have been provided or we have developed some catalysts that work very well in the lab, work very well with synthetic gases, but later they don't work well in real conditions. Okay, so this is one of the examples that the fuel works well in the engine and also make the catalyst to work better. Another example that I have brought here refers again to fuels and after treatment. In this case, it refers to a diesel particulate filter. So for some of you that are not familiar again with after treatment system, this diesel particulate filter again is a monolith that now is not dealing with carbon monoxide or one hydrocarbon, now is dealing with particulate matter. Then particles are coming from the engine and then particles are trapped in the filter. Some of these, we don't want that, but some of them, they might escape, okay? So what is happening is that particles get accumulated here. So there is some point that this particle filter is shouting you, clean me, because it's so clogged that it cannot deal with more particles and then it's producing some detrimental effects on the engine. So at that point, we need to regenerate this filter. How to regenerate? Simple to say, not so easy to do. Regeneration is a question of burning these particles that are already produced here. How to do that? Increasing temperature. So increasing temperature means you need to spend money, because if you want to increase the temperature here, either you have a heater to increase the temperature, so it costs you energy, or either you increase your temperature of the exhaust gas, that again costs you fuel to be able to regenerate that. So then in the past, again, we have came with some type of fuels. In this case, again, is biodiesel, but also butanol, also some alcohol type fuels, that they are in one hand able to be cleaner than diesel, and this is reflected here. If you remember the trade-off we mentioned before, I have brought here NOx emission level with respect to soot or particulate matter level. So we can see here that with diesel, we have several engine calibration approaches, and we are able to obtain different results in terms of soot and NOx, but we are not able to go in with diesel, we are not able to go inside this barrier, it's a Pareto front here. Then when we change the fuel, we are able to have a displacement of this Pareto front inside. What means for the same level of soot, we are able to produce lower level of NOx with respect to diesel. Or for the same level of NOx, we are able to produce lower level of soot with respect to diesel. Okay, so that means that this type of fuel has higher potential to be able to have lower potent emissions, but also we have studied how this fuel affects to particle characteristics, and then we came that our particles are easier to be oxidized. What means that when we have our filter closed with particles, it will be easier to oxidize them. So we will need to go to lower temperature, so less money, less energy, to oxidize these particles. Then another of the examples, this is hydrogen related, and this example has been funded during the year with Innovative UK EPSRC projects. And then this is, so we have this in the lab, so it's what we call a reformer. So how does it work is we are injecting fuel, could be gasoline, could be alcohol, and then we have this device in the exhaust. And then using some waste heat that otherwise will be released to ambient, we are able to transform, to upgrade this fuel to hydrogen. Then the whole idea is we are recovering this waste heat from the exhaust, and then we transform the gasoline to hydrogen, then we recirculate back this hydrogen to our engine intake, and if required, we also can recirculate back this hydrogen to the after-treatment system. What is the effect of that? The effect of that is if you take into account the total fuel consumption, so you will see how when you don't have this approach, you have this level of fuel consumption. Then when you use this approach, you reduce fuel consumption up to here. So depending on the engine or the driving condition, the reduction in fuel consumption could be around 10, 5, 9, 12%. Of course, this taking into account also the fuel that you have used to convert the hydrogen. So it's a global measure, it's a global system efficiency of the fuel that you are using. So it's good, it's able to reduce fuel consumption, so you will have an effect, a positive effect in terms of CO2 emissions. And at the same time, we also have measured particle emissions, and we can see here how this represents for each particle size, how much is your level of particles. So as you can see, the particle emission level with this system, with this reform exhaust gas recirculation, is lower for all particle size with respect to gasoline combustion. So again, we have another synergy on our double effect here. Another one here, also hydrogen related, is in that case, instead to use a hydrocarbon fuel, we can use ammonia. And if you realize, ammonia has no carbon, so the expected benefit will be larger. And ammonia has a lot of hydrogen. So ammonia could be understood as both as an energy carrier and also as a hydrogen carrier. So I have several options, as we discussed before. I could have my ammonia and inject directly in the engine, and then be able to use these zero carbon fuels. But sometimes ammonia has, or most of the time, ammonia has some challenges in terms of be burned in the engine. So what we can do is we can inject the ammonia with upstream a catalyst, and then this catalyst will decompose the ammonia in hydrogen and some unconverted ammonia. Then we will recirculate back this hydrogen plus unconverted ammonia to the engine. And if required, we can use also this mixture in the after-treatment system, if helpful, for the after-treatment system. So it seems a complicated system. So we have, during the year, we have been split the process. So first try to understand how is the reactions, later also try to understand how is the burning of ammonia or the burning of ammonia plus hydrogen. And then we understood that when you have hydrogen, it helps a lot to be able to utilize ammonia. And then some of the results are that we are able to reduce CO2 emissions, depending on how efficient is your decomposition process to hydrogen. You are able to replace more or less carbonaceous fuels, so you are able to reduce more or less CO2 emissions. And later, in terms of the after-treatment system, let's say this is the conversion of one after-treatment system without being injecting ammonia and hydrogen. And then we inject this mixture, we are able to improve the performance of the after-treatment system. So again, we found a fuel or energy carrier that is able to provide some benefits in the engine and also in the after-treatment system. And going to the second part of the talk is a bit more on particle characterization. Don't know if you are aware what is particle, but usually when you are with your vehicle and you are in a traffic light and you see that the car in front of you start, you see a black gas coming back from the vehicle in front of you. Then mainly this is composed by gas, but it's also composed of these small particles. Okay, so these are very small particles. It has the size is about micrometers, or even nanometers, and then usually it has an important health impact. Could produce cancer, asthma, diabetes, chronic bronchitis. Now people also are even related to COVID-19 because can transport the COVID-19 virus and also can exacerbate the effect of COVID-19. So after this brief introduction of what are particles, something that I have particularly interested to understand how is the shape and how much is the size of that particle. Why is that? Because depending on the size, depending on the morphology of the shape, they have different characteristics. They are more or less dangerous. So for example, when you have some particles that are large, like this one, they might be easily trapped in the human system, in the human respiratory system. Now, if you go to smaller particles, about 100 nanometers or smaller than 100 nanometers, then they might go deeper through the respiratory system. And then, if this particle are small and have a shape that are difficult to be trapped, they can go even inside your heart, you can be in your lungs, and they can go to even the blood, and it could be spread, let's say, around the body. So you see the size and the morphology impact on how dangerous are these particles. So in terms of particle characteristics, as we mentioned before, size, and usually represented by particle size distribution, so how many particles you have per size. Here, as you can see, the range is 550, 500 nanometers. We have also morphological and nanostructural characteristics. Morphological because in somehow it can tell us how easy it will be to trap those particles, and nanostructural is because they will give us some clues how easy it will be to oxidize these particles. And we also are able to produce evidences really on how easy are to oxidize those particles. Is how much is the temperature that you need to oxidize those particles. So I will go with one slide each. So how we are doing that in our lab? Okay, we have our engine here, we have our exhaust pipe here, and we have particle coming. Then the particles are coming, they have agglomeration with each other. We have a dilution system here, and then we are able to collect particles in filters, and we are also able to measure particle size distribution of these particles. Then we are able also to, before all these processes happens, to input in the exhaust one very, very small filter that later we go to the microscope, to TEM or high resolution transmission electron microscope or Raman microscope, and to analyze the morphology and the nanostructure. Or even with the filter, we can have further analysis and be able to understand the composition of the filter. In terms of morphology, when we have our filter, we go to the microscope, we obtain this picture, and then we need now some post-processing of these images. We have developed a homemade method using MATLAB that then is able to remove the background of the picture, and now here is able to identify radius of gyration relevant to the size of the particles, and also doing some further mathematical process, we are able to know how many particles, how many primary particles, let's say, how many small particles compose this big agglomerate size, and also fractal dimension. Fractal dimension is a mathematical parameter, is a quantification of the shape. So if fractal dimension is equal to 1, means that it's a chain. If it's equal to 3, means it's a sphere. So usually when you have a chain, it's easier to be trapped. When you have a sphere, it's more difficult to trap. So it gives us some guidance on which system to design to trap the particles and also how dangerous they will be. So we can go deeper in resolutions and we can make zoom to higher resolution, and we can try to analyze the structure, the nanostructure of those particles. And then we can quantify some of parameters that give us an idea how easy will be to destroy or to oxidize this particle. Okay, so when we try to analyze a new fuel, then we try to understand how are the particle characteristics and how easy or difficult will be to design a system to trap those particles, or how dangerous will be those particles for our human health. And then the further evidence is we are able to, we have an equipment, it's a thermogrammetric analyzer, and then we study the oxidation of those particles. So we have a filter with particles here. This is coming from a car, from a vehicle, and then we introduce this in a furnace, and then we increase temperature, and then we record how the mass is lost here. And then we can do further processing and we can get the derivative. So it's telling us, okay, for this specific case, to oxidize the particles, you will need to go to around 630 degrees. So if we are able to find fuels or systems that are able to go down with the temperature, it's even better, because that does mean that you don't need to go so high in temperature to get rid of the particle, for example, in particle filters. So this was a bit of what we have been doing in these last 10 years. I suppose that you are aware that in automotive power generation, the situation is changing a lot in the last years. Now people are moving away, let's say, from internal combustion engines, from diesel vehicles, from gasoline vehicles, and we are trying to introduce hydrogen, we are trying to introduce electrified powertrain or electrified vehicles. So as next step, we plan to carry on trying to identify the synergetic effect between fuel, powertrain, and after-treatment system. In terms of the fuels, there is an interest now in trying to use fuels coming from waste, or fuels that they don't have any competition with food or any competition even with land. So it's coming from waste. There is some problem. We consider them as promising fuels. So we need to understand later how they behave in engine, after treatment system, and so on. And we are also trying to give first step in zero carbon technologies, and I will have an example in the next slide, and also with electrified vehicles, either hybrid vehicles that have the combination of internal combustion engine and electric powertrain. Ideally try to bring the positives, not the negatives, the positive of both of them, internal combustion engine and electric motors. Then in terms of emissions, we are trying to not only work on emission coming from combustion, but also emissions from oil, also emissions from tires, brakes, and road that are getting very popular now in terms of automotive. And we have tried to expand and not only work on automotive related topic. So in the last 2 or 3 years, we have started to work on emission, in this case, indoor emission from manufacturing processes, so from 3D printers. So I have one slide each to finish the presentation. So regarding the zero carbon technologies, I didn't want to put a slide here of hybrids or electric vehicles, because maybe one of the speakers will talk more about that topic now. So I have here something that might be unfamiliar for most of you. Is a liquid air nitrogen powertrain. This is an engine that we have at the university. We did some research with it, and we plan to do some further research with it, that is able to work with liquefied nitrogen. So liquefied nitrogen or liquefied air does have no carbon there. So already we have some benefits in terms of CO2 on other pollutant emissions. Then it works like an expander. No, you have liquefied nitrogen. When you have a liquid, the volume that it takes is small. So the idea is you inject the liquid in an engine, and the liquid is converted, is very low temperature, minus something degree, to be able to have the nitrogen in a liquid state. When you introduce to the engine, there is an increase in temperature, then the liquid is converted to gas, and then there is an expansion process, so the gas expands and then moves the piston down. And then it's generating some movement, it generates some energy in the way that an expander works, or in the way that an internal combustion engine works. And then it's able to generate work. So the red thing here is a heat exchange fluid that is required to be able to the engine to work as quick as we need for an internal combustion engine, to be able to work around 2000 revolutions per minute. And the idea is to use this type of engine not to move only a car, but for one of the applications could be transport refrigeration units, TRU, that at the moment they are equipped with diesel engines that are not even regulated. So the idea is to use one of these engines to replace this diesel engine and to have a cleaner system again. And also because in these transport refrigeration units, we have the low temperature required to have this liquefied nitrogen. Another slide is about non-Nexus emissions that I don't know if you are aware of them, but are becoming very popular now. So I introduced to you a figure that shows the importance of those emissions since 2010 to 2020 and what is expected to happen in the future. So as you can see, the proportion of exhaust emissions is reduced. So this is consistent with the approach that I introduced to you before. Little by little, the engines are getting cleaner. We have this diesel particulate filter. Electrification is coming. So there are expectations that the level of exhaust or combustion-related particles will be reduced with time. But at the same time, there are expectations that the level of tire wear, brake wear, and road abrasion particles might increase. And there are some interesting discussion here about what will be the impact of electric vehicles, what will be the impact of autonomous vehicles on this type of emission. For example, and from my understanding, when you have an electric vehicle, I think that the brake wear emissions might be reduced because you have the regenerative braking, so you are able to use less the friction brakes normal that we have in our cars. But at the same time, with electric vehicles, the vehicles become heavier. So because the vehicles become heavier, most likely the tire wear and the road abrasion emission will be higher. So there is some interesting line of research here. And last slide, one of my last slides is about 3D printing emissions. So really this topic came 3 years ago when, in collaboration with some other group in the university, they have a 3D printer, and then they noticed that this 3D printer was having some vapors that make feel some of the people uncomfortable there. And then we decided, okay, let's try to understand a bit more what are these vapors, or what are these particles that are coming from the printer, and try to apply our expertise coming from automotive to this new application. At that time, there were not many papers published in the world in this topic, maybe 3, 4, 5 papers, not more. So we thought it was a novel topic worthy to investigate. Then I just put a picture here. I think it was in January, February, last test that we were able to do using a PLA. It's a, let's say, we call cheap, let's say, 3D printer that are using this plastic material, and then you have the plastic, you feed this plastic material, this filament, then you heat it, and then it's melted, and then it's produced the 3D printed components. So because there is a heated process involved with a plastic, most likely vapors are produced and most likely particles are produced. So then we brought our SMPS and then we tried to understand some 3D particle result there. So then this also, what are the conclusions that we have? One of the conclusions that we have was, and to me it's very interesting, is we try to plot with time the total particle level. And then we saw how at the beginning of the printer, while you have all people there with expectations, looking very closely to the printer because you are trying a new material or because you are trying to produce a new product, then you have huge particle emission level. However, after a few minutes, this particle emission level drastically decay. And then after a few minutes, the level come back to ambient conditions. So this again, it brought a lot of interest, again, due to COVID-19 reason, because there were many people trying to let's say, manufacture their own PPE using 3D printers at home. And of course, 3D printers at home, they don't have any filtration system, they don't have any cover. And then I support that printers were even in the room, in the bedrooms of the people producing this PPE. And I support that, I mean, I even watching the news in BBC, I saw how they were showing people producing PPE with 3D printing and how you have 5-10 people around the 3D printing when the process started. So it gives us the indication that there is not enough understanding in this area. So we have published recently a paper there, like how with very simple findings, like, okay, please don't be around the printer in the first minutes of printing. We are able to reduce hugely the exposure to this type of applications to us, let's say, or to humans. Well, I hope the presentation was not very boring. I hope that even though you have not automotive background, you were able more or less to follow the presentation. And in any case, if you have any question, I will be very happy to answer them. So thank you for listening.
Hello, Martin. Thank you. Thank you for our presentation. This presentation gives us many knowledge about IC engines. Yeah. We have one question from the attendee. I already unmute yourself. Hello, Pun. Yeah.
Hi,
I already unmute you. You can directly communicate with Martin. Yeah.
Okay, hi. Overall, it's an interesting talk, by the way. So my question is, as you, in the lecture, you mentioned one of the ways to tackle the greenhouse gas emission is to use low carbon fuels, right? So, but the price as a consequence will inevitably rise, of course. So do you think, like under this situation, will people be more likely to buy those more expensive but green fuels?
Yes, I wish I have the solution here, and then probably I will be rich already, no? if I come with the solution. But yeah, I think that there is something very, very important with respect to that is affordability. As you mentioned, no, the price might be more expensive. So I think that when we come with solution, we also need to make sure not only that they are clean, not only that they are renewable, or also that they are affordable for most of the people. And I think that, again, at the moment, there is a lot of incentives for the case of these zero carbon fuels, or for the case of electric vehicles, for example, to make them a bit more affordable at the moment. I think with the aim that with the time technology develop, and then they might be able to get cheaper. So I think, I mean, my point is that what might not be affordable today might be affordable in 5 or 10 years. So yes, you are right. I understand the concern, but I think that just stopping development because it's not affordable now is a bit risky and it's a bit dangerous. No? So it's better to give some steps and try to understand the science behind the potential, and then later evaluate, or in parallel evaluate, okay, is affordable now or it will be affordable for during the next year. And yes, we could agree or we could disagree, but I think this is the approach that is taken at the moment.
Okay, thank you.
Hello, Peng. Yeah, by the way, our second speaker, Michael Morgan, he will talking about converting the biomass to the alternative fuel. I think maybe in his presentation he will include some technical solution, and also the if we can see if he also provide some cost-effective manufacture pathway of the fuel, the alternative fuel. I think you can keep attention to our second speaker, because I think he will also give you another insight about the fuel production. Yeah, any question from our attendees? Please raise your hand. I will unmute you. Yeah, Martin, I have a question. Even though I'm also studied the IC engine, to be honest, I'm not very knowledge about what is the difference between the particle morphology and the nanostructure. What is the difference between them? I think this is also our attendees also have this question. And I saw in your slide you already listed some parameters about how to quantify the nanostructure. Can you explain to us a little bit about this question?
Yes,
thank you.
Yes, yeah. Yes. So I think first is a question of scale. So when you have a particle or an agglomerate, morphology usually refers to micrometers or hundreds of nanometers. However, when you go to structure, you are talking about 1 to nanometers. So the first difference is a question of scale. No? So you can use a transmission electron microscope to study the morphology or the shape, while then you analyze how these small primary particles group to each other. So it's the shape of the agglomerate, while nanostructure is now you focus on each of those primary particles and you go deeper in them to the 1 to nanometers level, and you see how the graphene layers, to be more specific, are disposed within the particles, within the nanoparticle. So one difference is in terms of the scale. Second difference also is nanostructure usually is defined in the combustion chamber. To modify nanostructure, you need very, very high temperatures. So once the particle is formed in the cylinder, nanostructure might not be modified anymore. However, morphology, you can modify. Morphology is modified through the travel of particles in the exhaust and through the travel of particles even in the atmosphere. So nanostructure is not going to be modified anymore. It is defined in the combustion chamber, while morphology will be different along the exhaust system. So the third difference also is why those are important. So nanostructure usually provide us information on how is the formation of particles, how has been the formation process in the cylinder. And usually it's related to particle reactivity, how easy will it be to oxidize this particle, while morphology does not provide so much this information and provide to us more information about the how difficult or how easy it is going to be to trap these particles. So as you can see, there are many differences in terms of size or scale. You are working in different size scales, different scales. In terms of why it's important to study one of the other is also important, and the information that provides to us. Have I answered the question, Runsao?
Thank you. Yeah, we have Leo attendees. Wait a minute, I just meet him. Yeah, I also have another question. It is that what is in your slide there is a slide illustrate the soot oxidation patterns. I wonder what this soot oxidation pattern curve can provide us, and how do we interpret this data to reflect on our combustion process in the engine?
Yeah. I'm trying to share, but I don't know if I can. Since you are referring to that, no, Runsao? Can you hear me? Can you hear me, Runsao? Hello, Runsao, can you hear me? Or can anyone hear me?
Oh, sorry, I mute myself.
Okay.
Yeah.
Sorry, I didn't know if, because I tried to share the screen, but then I didn't notice
when
it.
you share your screen, I mute myself. Yeah.
Okay, sorry.
Yeah, we saw your screen. Yeah.
Let me try to do it again.
Yeah.
Yeah, I think that you are referring to this plot. So what is telling us is how when you have some particles.
Yeah. This plot, yeah.
This one. Later you increase temperature, then we see how the particles get oxidized. So what they are telling us is how easy or how difficult will be to get rid of those particles when they are already trapped in a particle filter. So as we mentioned before, you have a filter in the exhaust. The filter is getting accumulated with particles. At some point, you have too many particles there, and you cannot accumulate anymore. Then at that point, you need to clean up all those particles from the filter. How to clean up? You need to increase temperature to be able to remove all the particles. So this plot is showing us the temperature that you need, for example, to remove let's say 40% of the particles, or 50% of the particles, or 90% of the particles. And this is the derivative. That is the derivative of this plot that is showing to us which is the temperature that you have the maximum mass loss rate of particles. So it's telling us, okay, at this temperature, you are really efficient cleaning the DPF, cleaning the filter. So if you have particles produced by different fuels, then instead of having this plot here at these temperatures, have the plot at here, 400. That means that for that case, you will be able at 400 to clean the filter, while for the particle in the slide, you need to go to 650 to clean your filter. So for example, with the use of alcohol fuels, the particles that are emitted, when you do this type of analysis, you observe how they are easier to be oxidized. So this plot will be here. What means instead to go to 650, if you go to 500 or 550, you will be able to clean your filter. And there are some other researchers that they are trying to add some catalysts to the fuels that to be able to create particles that are able to get easier to be oxidized. So to move this to the left.
Thank you, Martin. Yeah, that means this we can use this data to know which temperature window it is the most efficiency, efficient to regenerate the DPF. Yeah. Okay, thank you. Any questions from our attendees? Please raise your hand. I will unmute you. Yeah. If it is no question, we can have a break. Thank you, Martin. Yeah, thank you for your wonderful presentation. And thank you to all.